All right, so we're doing problem 3 of chapter 27, and that question asks what the strength and direction of the electric field is in this diagram. And in the diagram, there's a positive 3 nanocoulomb charge on the same line as the point we're looking at, and that is 5 centimeters away from the point. And then there's a negative 3 nanocoulomb charge, which is also 5 meters away and 10 meters below it. So that's the diagram. And here's a little more of a zoomed in kind of diagram on the point, and that shows the electric field in each direction. There's the x and y components of E2 from the negative charge, and then E1 only has an x component because it goes directly straight on the same axis. All right, so first we're going to find that angle theta, and by doing that you're just going to take the tangent, or the inverse tangent of 0.1 meters and 0.05 meters, and that'll give you 63.4 degrees, so that's theta. And then, so then we can start doing our Coulomb's law equations, and we'll start with the positive charge, and so that's E1, and just KQ over R squared, just plug that in, plug in 0.05 for R, and then that'll give you 10,800 newtons per coulomb, and so that's E1. And E2, you can use the same equation, KQ over R squared, and do the absolute value because you can kind of use common sense to find the direction of the charge or the electric field that the charge gives off. And the R is a little bit different because you have to use Pythagorean theorem to get that R because of the angle. And the squared and R squared will get rid of the square root that the Pythagorean theorem gives you. So you have 0.1 meters squared plus 0.05 meters squared on the bottom for R, and that, plug in the calculator, will give you 2,160 newtons per coulomb. So we have our E1 and E2, and we can go ahead and put this in X and Y components to find the resultant magnitude just one step closer. And for in the X direction, we're gonna do E1x minus E2x, and since they are pointing in different directions, that's why the minus sign is there, because E2 is a negative and it'll be the opposite way of the positive charge. So, and for E2, we have to use the cosine of the angle because we have to split that one up into components because it's not on the same line as the point. So we plug that in, E1 minus E2 cosine 63.4. There's E1 and E2 times cosine of 63.4. And that will give you a result of 9.83 times 10 to the third newtons per coulomb. So that's our electric field in the X direction. And then the Y direction is a little bit easier because there's E1 will go to 0. And E2, you just do that E2 times the sine of 63.4 degrees. And that number right there will give you the complete Y direction of the total electric field, and that is negative 1.93 times 10 to the third newtons per coulomb. And so that's our X and Y components. And from there, it's pretty easy to find the magnitude. You just do, you just have the square root of 9.83 times 10 to the third squared plus 1.93 times 10 to the third squared, and that will give you the magnitude. And that'll come out as 10.02 times 10 to the third newtons per coulomb. And then the last part that we need for the question is the direction. And we already used theta, so we'll have alpha equals the inverse tangent of the y component over the x component. And you can just see that from the triangle. And then, so you plug that in. EY is negative 1.93 times 10 to the third newtons per coulomb. And then EX is 9.83 times 10 to the third newtons per coulomb. Plug that in, you'll get 11.1 degrees, and that is below the x-axis and to the right. So that's it. It's a pretty simple problem. And